I'm going to show you some interesting ideas about calculus. It's a little bit of an unusual video, so let me tell you what this video is actually about. It's about three different things. One is to try to provide for you an interesting way to think about and understand calculus beyond the normal types of equations you see in a calculus textbook here for the derivative, to give you some insight into what calculus is all about. And take that insight and allow you to see how it can actually be useful. Because in fact, calculus is used every day by lots of people to do very important and useful things. And thirdly, to show how when people do that, they typically will do that using a numerical method. And what that means is to take the calculus that's being used to do something useful and put it on a computer so that you can solve it very, very rapidly. It allows you to solve real-world problems that don't fall into a simple pattern that you might have in a textbook. And that'll give you the big picture of what calculus is all about. That's the goal of this video. Okay, so let's think about how that works. In a usual textbook, you might have equations like this, where you have a simple algebraic equation, some other tricks, square roots and absolute values, maybe use a quadratic formula or some other type of trick to solve an equation. And these homework problems are constructed to teach you the rules of algebra or trigonometry or whatever it is you're learning, and maybe some tricks to solve these types of equations. Well, in the real world, often you are not so lucky to have an equation that can be solved that way. And so just as an example, suppose I take these sets of equations and just make a small change, like put a 4 here, put a sine x here, make that x a tangent x, make this a 7, make this a square root, put a 3 here. Suddenly these equations become very difficult to solve, and the usual tricks that you learn for your homework problems simply don't work in the real world. And so in the real world, you are faced with a set of equations like this that you need to solve, and you need to have a way of doing that. And it turns out that even though these look like algebraic sorts of equations, the best way to solve them is actually to use calculus and to do it on a computer so that you can do it very, very rapidly. Because sometimes you have to do it many, many, many times. So the way we do that is we take these equations, write it in this form, and then we can use calculus to solve it. So let's see how that works. Okay, first of all, this is called finding the root. What we do is finding the root is we have an equation f of x equals 0, and we're going to try to solve it to find the root. So what does this mean? What it means is if I know what the root of the equation is, and I put that into the function, it's going to give me 0 back. So the root is the value of x that when I evaluate it with the function gives me 0 back. Very, very general type of operation I might want to do. So you're probably asking yourself, what if my equation doesn't look like this? A lot of the times you can write it to look that way. Suppose you have some left-hand side h of x, some complicated thing, polynomial, who knows what it is, the g of x on the right-hand side, exponentials, square roots, absolute values, doesn't matter. What I do is I subtract g of x from both sides, write it like this, call this combination here f, and now this equation, whatever it happened to look like before, now looks like this equation. So I can take a wide range of different equations and rewrite them so they all look like this, and then I can attack it with the same methods from calculus that I'm going to show you. So let's get started and do that. Okay, now before I do that, I want to talk about a second goal that we might have, and that is to find either the maximum or the minimum. Instead of finding where a function goes to 0, another class of problems we might want to solve is when we want to find the maximum or the minimum of a function. And this is using calculus twice, which is kind of interesting because calculus tells us that where the maximum and the minimum are is when the derivative of the function equals 0. So that uses the derivative from calculus, and then, as I'm going to show you in this video, I can then use calculus to solve the resulting equation because this has exactly the same form as I had before. Now, when would you want to do this? Well, to make the world a better place, we often want to solve a type of problem called optimization, which is to find the best element in a set of elements. That sounds abstract, but very often what it means is finding, like I said, the maximum or minimum of a real function. So that's the two problems we want to be able to solve. When is a function equal to 0? That solves any kind of algebraic equation. Or when is it optimal? When does it have a maximum or a minimum? And these two things come up so often in real world, it'd be impossible to even list all the different places where these types of equations need to be solved. So how can we use calculus to help us solve these problems? Okay, we're going to start off now with a very simple method that doesn't use calculus at all, because I want to show you how when we use calculus you get answers very quickly and much more accurately, and that shows the power of calculus. So we're going to start by doing this without calculus, and we're going to start with finding the root of a function. So the first thing we do is we can look at our function f of x versus x, and the first thing we're going to try to do is bracket it. What bracket it means is the following. We want to have a value on the left and a value on the right such that we know where the root is. The root is right here. We're trying to find that. What is that? By bracketing it, we have a value on the left and a value on the right, and we know the answer is in between. We want to do that. Okay. Then what we do is we simply divide the interval into small pieces. We just divide this up, and as we divide it up, we're going to look to see where it changes sign. So we start a march. We start here, divide the interval into these little pieces, evaluate the function, keep evaluating. It's up positive, it's positive, it's positive, it's positive, up, and now it's negative because it crossed 0. So now I know the answer is between these 2 points. And then what I do when I'm done is I simply average those two values, because I don't know if the root is actually closer to the left or to the right. So just as a good guess, I just average it and find the value in between, which in this case is actually very close to the right answer. Now if that's not close enough, you can divide it up into even more pieces, and maybe to get a really good answer you need to divide it up in maybe 20 or more different intervals. And it's a very simple thing. You could tell a computer just to do that. Very simple. Just keep evaluating on smaller and smaller intervals until I get as close as I want. Probably need, more than 20 function evaluations to do that, but it's very straightforward. Okay, now let's look at another method that's a little bit more clever. What we're going to do is we're going to use the bisection method. And the bisection method, what we do, bracket the root again, just like before, but now what we're going to do is divide the interval in half. So rather than just slicing this up uselessly, we're going to just try to rapidly figure out where this guy is by dividing in half and dividing in half and getting rid of parts of the interval in big chunks. And again, look for a change of sign, repeat, and then take the average. So the first thing we do, divide it in half. Now I've completely ruled out that the root is anywhere in here. That's pretty good. Divide it in half again. Now I've completely ruled out that it's anywhere in here. And the way I know which side to divide it on is I have to make sure that one side is positive and the other side is negative. So now I need to divide it in half again. And now I've completely ruled this out, divided in half again, and you can see I've ruled this out. And now I know the answer is in here. I can take the average of the left value and the right value and get a pretty good answer of where that is. And I had to evaluate the function 1, 2, 3, 4, 5, 6 times. So of order 10 times, which is about half as many as I needed for the other method. Approximately, and I'll get into some more details about that. But you see the basic idea. Okay, now let's compare those two and see what's really going on. So far we haven't used any calculus. Here's where the calculus starts to come in. Okay, what we notice as we were doing that, if you were really paying attention, is as we got close to the root, the curve started to look like a line. So as we went from here to here to here, once we got all the way down here and we had the root bracketed, What we did is we took the average of the left and the right. And in this case, that was pretty good. The average was about right here, which is pretty close to the root. Not too bad. If we looked at the bisection method, it didn't work so well. If this was the left and this was the right, the average would have been right here. But we noticed that this looks kind of like a line in here, and it looks kind of like a line in here. And this is the key. What we're going to do is we're going to write the equation for a line. And I'm using an abbreviated notation here like this, so I don't have to write this out every single time. So YL is the Y value on the left, YR is the Y value on the right, and then XR, XL, the values of X. So you can see this is the rise over the run, and this is the intercept right here. So this is the equation of this line. And now finding the root of a line, I can just do algebraically, and I can write the answer down once and for all. So once I've done my incremental search and narrowed it down to this interval, I have a really good estimate. I basically am saying there's a line between here, and the root of that line is the root of the overall function. Very close. Here it works really well because it actually figures out that the root is way over here on the right, which is very nice. And so by using this, I can actually get my final step can be much, much more accurate than this. Now, what we're using here is the concept of a limit, which is one of the key concepts in calculus, which basically says that as you break up the interval in smaller and smaller and smaller pieces, it locally, near the root, starts to look linear. And once it's linear, I can use the concept of a slope that I already know from just algebra, from what I know about the property of lines. And this is one of the main ideas of calculus. Now in calculus, we often use this idea of a limit and this slope to give us things like the area under a curve or the slope of a curve or the length of the line or whatever. Here we're actually using it to solve an equation. Sort of another way of using calculus, but using the same idea of a limit. Allows us to solve equations. Okay, now that we understand that this is calculus, we can actually start to invent new methods that are very much more accurate and really start to use calculus a lot. Okay, so here's the basic idea of what's called the secant method. Okay, if our two initial points are very close, as we saw, a line approximates the curve between those 2 points. That was this improvement that we figured out by putting a line between the 2 final points, finds the root much better. Okay, from the equation of that line, we find where it crosses 0, and so where the 0 of the line is very close to where the 0 of the function is, because if I bracket it really small with a small interval, the function is approximated by a line. That's what calculus tells us in that limit. It's the concept of limits. So this suggests making a new method based on calculus that says let's just start with a line in the first place. So the idea is to just take the function here, the blue function, and say, well, it approximately looks like this red line, and just start with that to begin with. So let's see how that works. It's worth noting that before I show you how this works, it's worth noting that this idea for finding the solution of a function, defining the root of a function, was actually invented thousands of years before people knew about calculus, which is very interesting because if you think about when calculus was developed by Newton and Leibniz and so forth, they knew about these basic ideas. People were using the concept of calculus long before it had been formally developed. Okay, so this leads us to a new method called the secant method. Secant method is very, very powerful, and it uses calculus. Here's how it works. Find 2 points near the root, and it helps if the root is bracketed. So typically, as before, we assume that we know the root is somewhere between these 2 points. And what we're going to do is find the root of the line that goes through those 2 points. So let's draw a line, which is this green line is approximately what this blue curve is doing, right? It's not too bad. And then what we do is we can easily find the root of that line. That's easy to do with algebra. And I get this point right here. And it's not, you might say, well, it's not exactly very close, but that's just the first iteration. Now what I do is I take that as my new point here, and because this one's positive and this one's positive, I'm going to get rid of this one because I want to have a positive and a negative to keep it bracketed. And now what I do, that's my new point. Now what I do is I draw a line between the two new points, and that's the repeat part. So let's see what happens. So there's my new point. I draw a line between them, and you can see I get a new estimate for the root, which is right here, a little bit to the left of the real one, but it is extremely close. And if I do that one more time, it is, let me clear this so you can see it. It is so close that you can actually, it's essentially perfect. And so what I had was about 5 iterations using this idea, about 5 iterations, and it's almost perfect. The other ones I was using 10 or 20 iterations and usually not getting this close. So by using this idea, you can just see how powerful the idea of a limit is. Okay, before we go on, I want to talk about the intermediate value theorem, because when you learn calculus, you often learn these theorems. They probably seem a little bit obscure. Why does this matter? The intermediate value theorem is very important, and it's the reason that all these methods actually work. So let me just talk about that as a little bit of an intermission here. Suppose I have a function defined between some value x left and x right, and it has a value f of x right here and a value here f of x left. What the intermediate value theorem tells us is two things. Is if this is a continuous function, then the value that the function can take between those intervals must lie in this range. In other words, it's between here and here. And we're using this fact when we talk about bracketing. It says that if this is positive and this is negative, the intermediate value theorem says that if this is a continuous function, I know that the answer is somewhere between these 2 points. Somewhere, if this is positive and this is negative, somewhere in this interval, it goes through 0. It's not going to be out here. So for example, what's very powerful about this, if you look at the secant method, if I draw a line like this, it goes through 0. I know, because this line is in this interval, that the 0 the secant method finds is going to be in this interval, and therefore the new point is going to be in this interval, and I draw a new line, its value will be in this interval, and I never leave this interval. That's a very powerful thing, because you wouldn't want it to start searching out here or searching over there when you know the answer is over here. And that's based on the intermediate value theorem. The other thing that it is important, we talk about functions that are continuous versus non-continuous, and you think, wow, who cares? Here's why it's very important. Suppose I have this function on the right, which is actually tangent, and I want to find the root, this root right here, and this function is discontinuous. So suppose I start here and I start here, and I use, say, the secant method. I'm going to draw a line like this, goes through 0 here. I get this as my new point right here. This is negative, and then I'm going to lock in on this point over here. So because it's discontinuous, you can see I actually find the wrong root. This is the one I'm actually looking for. But obviously, if I had started over here, where it's continuous between these 2 points, you could see how eventually I would lock in on the correct answer. So this is why whether the function is continuous or not is actually very important. So this is just a little side note of why some of these theorems in calculus are actually quite important. Okay, now let's move on to the Newton method, which is the most powerful of the methods we're going to use, and it uses calculus directly. Once you've seen what we just saw, it basically suggests the idea of using the derivative from calculus to solve equations. So how do we do that? So what we found was that the best way to find a root is that when we had gotten very close to where the root was, we noticed that we could fit it to a line and get a very good estimate of where the root was. Instead of using the average of XL and XR, we could actually fit it to a line and get a pretty good estimate. Okay, now what I'm going to do is I'm going to write these y's in terms of f's, which is the same thing, just so it's more obvious what I'm doing. It's the same thing. And then what I'm going to do is I'm going to say that the width of this interval, I'm just going to call it h, so that I can write that the right-hand side of the interval is equal to the left-hand side of the interval plus some h, just to make it kind of simple. And then I'm going to plug this into here. Now remember from calculus that the definition of a derivative of a function is the limit as the rise over the run over that interval obeys this limit formula. So if I use this fact from calculus, the best root I can find, notice that what this is right here is 1 over the derivative. So what I get is that a better formula for the root uses this, which is basically taking the limit, which is what calculus is, to go from this formula to this formula, which is I take the value at the left-hand side if I know what the value of the function is there, which is this, and I know what the slope or the derivative is there, I can project to find a really good estimate for the root. And then because I'm doing this in a computer, I can just iterate. N equals 1 gives me a new value for n equals 2. N equals 2 gives me a new value for n equals 3. And I just keep repeating this operation till I'm done. Now what's amazing about this method is it has two different features. One is it begins with 1 point, not 2. I only need to provide the value on the left side of the interval. But I also need to know the derivative of the function as well. So I need to be able to evaluate this derivative. And that's where calculus comes in. Now, let's see just how that works. Imagine I start with this point. Since I can start with any point I want, I'm not necessarily trying to bracket anything anymore because I can start with 1 point. So I'm going to start with this one. And I'm going to figure out what f is here, which I can get. That's just this value. And I can figure out what the slope is here because I can find the derivative. From that, I can use this formula to get my estimate for what the root is. And it doesn't look all that good on this iteration, but now what I do is I take that, feed it back in, and do it again. So now this is my new starting point. I find the value of the function here, and I find a line that goes through this. Now in this case, you can see the line that goes through it is so perfect. You can see the line up here is so perfect it's almost indistinguishable from the function itself. So now I hit very, very close to where that root is. It's almost perfect. And if I do it again, it is essentially perfect. So now what we see is we have 3 function evaluations, and we basically find the root almost perfectly. So what we can see here is that clearly calculus wins. So by using calculus, we can solve equations extremely rapidly and extremely accurately. So think about it. Which would you choose? Here's the 4 methods that we considered: incremental search, bisection, and calculus based. And it's very clear that the number of this one took about 20 function evaluations. This took about 10. Secant took about 5, and Newton took 2 to 3, depending on how accurate you wanted it to be. Now what's amazing about the Newton method is I started the guess over here simply so you could see what it would do. If I had started it on this side, like right here, in basically 1 step, it would have basically found something very close to the root. So you could even, if you had a better guess, you could actually do this in maybe 1 to 2 iterations compared to 20. And basically this proves how calculus can be so useful relative to this, which now probably looks kind of silly now, just to blindly just march and keep searching. Calculus tells us something about the function and the slope, and as we get closer and closer, we start to approach a line, and therefore the Newton method, every iteration becomes even more accurate, and it gets even closer at every single step. So every step, the next guess is a lot better because I'm closer to a line. The next step, it's even closer to a line, and at some point it's almost perfect, and you get there very quickly. Okay, so let's review that. Calculus enables us to find the slope of a curve, and we use that as a way of finding the best guess for where the root of a function is. In other words, solving an equation that's very difficult to solve otherwise. Now, that uses the concept of a tangent line. That's what this green curve is called. And in fact, all these curves have a lot of tangent lines. And so this curve right here is actually the derivative of the blue curve. So you can see all the slopes here are positive and the black curve is positive. Here all the slopes are negative and the black curve is negative. Here all the slopes are positive and the black curve is positive. So this is a plot of the slopes. And so we can actually look at all possible tangent lines and allow us to solve this optimization problem for finding the best value of something. Okay, so let's see how that works. What we do is we search through to find all possible tangent lines. That's what we want to search for. Just like we searched for the 0, what we want to do is do this, but instead we're going to search for the maximum and the minimum. So let's see how that works. This is the second type of problem. So let's try it. Okay, so we have to pick a problem. And so imagine that we're called in by the President of the United States who wants to throw this football, and he's going to be doing it in public, and he wants to throw it as far as he can. And so he asks us to tell him, how can I throw this football as far as I possibly can? So here's how we're going to do it. We're going to use a little physics, and if you can't follow the physics, that's okay. Just follow the logic and the ideas of it if you can't follow the physics. And I'm going to point out mainly the mathematical steps that are involved. But if you know some physics, you can try to follow along. So this first equation right here is the equation for the position of the football as a function of time. This is the initial velocity, and this is the acceleration, which in this case is only due to gravity. Okay. Now this equation I can break up into the x position, which is in this direction. Sorry, Barack. And the y direction, which is this. And so I have these two equations for the x and y position. The other thing that I've done here to make it simpler is I've broken this into the speed, the magnitude of the velocity, which he can control with his muscles, and we can tell him what to do there. And then we can also tell him the one thing he does have a lot of control over is the angle at which he throws it, which I call theta naught. So this describes the trajectory of the football. We want him to throw it as far as possible, which means making x as large as possible when y is 0. In other words, when it comes back down and hits the ground. So we want x to be large when y is 0. Okay. Now what you see from this equation is very interesting. This is a quadratic equation in time, which means that this goes to 0 at two different times. One of them is very obviously t equals 0. That's the initial time. That's right here, right before he throws it. And we can solve this equation for the other root. This is just the quadratic equation, and find the time when it hits y equals 0, which is if he throws it, it's going to go up and it's going to come back down. And that's going to be right here. And we can find from this equation when y equals 0, we can solve for t when t is not equal to 0 and find the time at which it hits this point. If we know when it hits that point, we can then stick it into this equation and find out how far it went. And we want that x to be as large as possible. So skipping some steps, you can do these steps yourself if you're interested in the physics. Doing that algebra, I find that the distance that it goes, the maximum distance it can go for a given v naught and a given theta naught is given by this value. So one of the things we can see right away, we can tell them is throw it as hard as you can. Use your muscles to throw it as hard as you can. That's one thing that's very clear. Gravity will make it go less far, but you don't have much control over that. So that's kind of obvious, but what's less obvious is that he can control the angle, because he can control what angle he's going to throw the football. But which is the best angle to throw it at? So what we do, this is our function of x, but now what it is we're going to solve f of theta naught equals 0, f prime of theta naught equals 0, to find the optimal angle for him to throw it. So that in this notation, that looks like this. take the derivative. We get this. You can work out the algebra, do the calculus yourself, and set it to 0. So this is a statement of the optimization problem. This tells us which theta naught makes x max largest. That's what we want to tell him. Now, that uses calculus, because this optimization condition is calculus, but we can also now use the secant method, we can use Newton's method, bisection method, the incremental search method. We can use that to solve this equation. This uses calculus twice to solve this optimization problem. But just for illustration purposes, I chose an example where I don't need to do that, just so you can see how it works without having to actually use a computer and use one of those methods. But in general, in real life, if you had, for example, air friction or some other problem like that, you probably would have to use one of those other calculus-based methods like Newton's method to solve this. But in this case, it turns out this equation can be solved, and you find that sine theta naught has to be square root 2 over 2. And that can be solved using your calculator. If you put it in the right units of radians, the theta naught has to be pi over 4. And if you use one of the numerical methods of Newton's method or secant method, it would probably very quickly give you a solution very close to this. So it's kind of interesting. What it tells you is that the president should throw this at an angle of pi over 4. Should not throw it at a lower angle and should not throw it at a higher angle. There's actually an optimal angle to get it to go as far as possible. And so let's just get a picture to see sort of how that comes about. And there you can see, if you throw it at an angle of pi over 4, it goes the maximum distance. Throwing it too high or too shallow, it will always go less far. And there we've solved the problem for our president. Okay. So with that, I hope you can see the big picture between what calculus is and how using derivatives and slopes useful for understanding what the functions look like and how we can take advantage of that to solve real-world applications like solving equations, solving optimization problems that are really important in the real world, and how putting those on a computer allows us to rapidly solve those problems and get very accurate answers for most problems which don't look as simple as homework problems that are in the textbooks. So I hope that gives you a bunch of insight into what calculus is all about and why it's important and why it's a very interesting thing to learn. Okay, and with that, I hope to see you here at New Planet School very soon.